welcome back, folks, and the topic of today's video is going to be a simple introduction to the quantum mechanical model of the atom. Alright, so why do we need a different model? Obviously this is going to be something different from the Bohr model that we were talking about. And we saw that in class the Bohr model did a really good job of explaining the line spectrum that we see for the hydrogen atom when we get it into the excited state. The problem, though, is in reality, as soon as I add a second electron to the system, so for example, if I want to look at an emission spectrum of helium, which now has 2 electrons associated with it, we find that the Bohr atom, or rather the Bohr model, no longer works. We can no longer use that simple model to now predict the line spectrum for a 2 or more electron atom. So the Bohr model falls apart. So what that means is that we either have to modify that model or throw it all out and start over. So shortly after Bohr introduced his model and people understood this limitation to the model, it turned out that folks tried to now tweak or develop the Bohr model to explain multi-electron systems. In the end, it just didn't work. All right? So a little bit later on, 2 scientists by the name of Schrödinger and de Broglie came up with what we now call the modern quantum mechanical model of the atom, which does a much better job of explaining the line spectra of multi-electron systems. So we need a little bit of background on this first. So one of the basic tenets of this new model that we're going to talk about is that we have to assume that the electron, which is a tiny particle, is going to have wave-like properties. So it kind of makes sense. If we take a look at our assumption here, we said that if we're talking about a photon, we said a wave can actually act like a particle. We said that's the particle model for light. That's the photon model of light. So if we assume that to be true, there's no reason why we can't say that a tiny particle, like an electron, ought to be able to have wave-like properties. Okay? So as long as the particle is a really, really tiny thing like an electron, we can say that that particle is actually going to act like a wave. So it's sort of our photon model in reverse. All right? Now, if we do this, we can come up with this thing called the de Broglie wavelength. Now, what the de Broglie wavelength is it's the wavelength associated with a moving particle. Okay, so the assumption is that if I have a particle or some sort of mass, that mass, when it's moving through space, will have a wave associated with it, okay, of a particular wavelength or frequency. So how do we get to the de Broglie wavelength in terms of a useful equation? Well, we can take advantage of equations that we already know. So for example, we know Einstein's equation here of E equals mc squared. That's the relationship between energy and mass. And we kind of say that energy and mass are interconverted by way of a proportionality constant, which is the square of the speed of light. So that's Einstein's famous equation. The other equation we're well aware of is the equation representing the energy of a photon, E equals h times nu. So since these are both energies, I can set these two things equal to each other here. So I can see that the energy in terms of a photon can be equal to the energy of a particle in terms of mc squared. All right? So now what I'm going to do is I am going to divide each side through by a c. Okay, so I can divide this side through by c, divide this side through by c. When I do that, I get an h nu over c is equal to an mc because this c cancels with that guy, leaving me an n times a c. All right? Now, why do I bother to do this? And the reason why I do this is because now we see that the product of the mass and the velocity, right? This is a velocity because it's the speed of light, right? So if I have a particle moving at the speed of light, this would be the velocity of that particle. So a mass times a velocity is known as a momentum. And I'll give momentum the symbol of a lowercase p here. Okay, so that's just a physics definition, classical physics definition. All right? So now what I can do is I can say that p, or momentum, is equal to h nu divided by c. All right? So that's my momentum now in terms of frequency, Planck's constant, and speed of light. Now what else do I know? I also know that nu is equal to c divided by lambda if I'm talking about a wave or photon of light here. Okay? So I can make that substitution. So I'm just going to take the c divided by lambda here, and I'm going to substitute it in for the nu. When I do that, this is the relationship that I get. hc over lambda divided by c. Now, you can see that the c will cancel out. I've got a c there, and I've got a c there. So if I cancel those two c's out, now what I've got is momentum is equal to h, which is Planck's constant, divided by the wavelength of the light. All right? So now all I got to do is solve this thing for the wavelength. If I do that, the wavelength becomes the ratio of Planck's constant to the momentum. I can also put momentum back in terms of mass times velocity. So if I do that, I end up with lambda is equal to Planck's constant divided by the product of mass and velocity, which is going to be my momentum. All right? So this lambda here that I've now solved for is known as the Broglie wavelength. So that's going to be the wavelength associated with a particular particle moving at a particular velocity. Now the importance of it is that, again, the particle has to be really, really tiny. Okay, so I could have, for example, a big object like a person or a baseball or something like that moving at a particular velocity, and I could calculate a Broglie wavelength associated with that. So we might actually do that in class. And what we're going to find out happens is that the wavelength that we end up calculating for a big, slow-moving object really doesn't have any pertinent meaning for us within the electromagnetic spectrum as we've discussed it in class. So it's a meaningful wavelength, or a meaningless wavelength. So I could calculate my own de Broglie wavelength, but it would have no meaning because it doesn't fall anywhere along the known electromagnetic spectrum. But if we do it for a very fast-moving electron, okay, that's a different story. Then we could actually have a meaningful de Broglie wavelength, where now that particle actually has true wave-like properties. All right, so if we keep in mind the assumptions about the de Broglie wavelength that we were just talking about now, we can use that to now build up the assumptions of our modern quantum mechanical model of the atom. All right, so here are the assumptions. Again, the model was developed concurrently by de Broglie and Schrödinger, so it's sometimes called the de Broglie-Schrödinger model. But here are the assumptions of that model. The first one, as we just discussed, the electron in the atom is going to have wave-like character. So the electron is going to behave like a wave. All right? Now, some of these things sort of go hand in hand with the Bohr model that we talked about, and the next one does. So we can also say that for any given electron that we're talking about, the electron's energy is going to remain quantized, just like it did in the Bohr atom. Because remember, we said that in the Bohr atom, an electron can only have a particular energy associated with it, which is based upon which orbit it happens to be in. Okay, so we take that same sort of idea with us as we move into the modern quantum mechanical model here. The next thing that we have to think about is that the electron is going to be housed in a three-dimensional volume, which we're now going to call an orbital. So we can kind of think of an orbital as being a three-dimensional region in space that's kind of like a Bohr orbit. Okay? So now rather than thinking about the electron just being in a simple two-dimensional plane, now I can think about the electron as actually taking up space within some three-dimensional volume. Okay? So in honor of Bohr and his orbits, we're going to call that three-dimensional volume an orbital. Next, we can state something about the electron's position and its energy based upon statistical probability. So when we start assigning, for example, an electron to a particular house or orbital, we can't say with any given certainty that the electron is actually there. We're just going to say with some degree of statistical probability, we believe the electron to be there. Okay? So that's another assumption of the model. And then finally, we can say that each electron in the atom is going to be characterized by some unique set of quantum numbers. Now thinking about the Bohr atom, we know that we could assign a quantum number to a particular orbit. All right? But in this particular case, what I'm now going to do is assign a set of quantum numbers to the different electrons in the atom, and each electron in the atom has to have its own unique set of quantum numbers that makes it different from any other electron that's also in the atom. So this is a lot to digest. So what I normally like to do here is I like to kind of get a pictorial representation of what an electron in an orbital might be sort of represented as. So what I like to do is I like to think in three-dimensional space here. So I'm using Cartesian coordinates, x, y, z axes that lets us deal with 3 dimensions here. And what I'm going to do is I'm going to sort of define a region in space. I define it as a circle here, but since we're also talking about a z-axis, we have to think about this as more or less like a ball instead of just a simple circle. All right, so this is a 3-dimensional circle, which is really just a ball or a sphere. So now, what we think about here is we think about the electron with its wave-like properties inhabiting this sphere. So I could put the electron, for example, right here. Okay, so it's inside the shell of the ball, if you will. Okay, and I could say with some degree of statistical probability that this is where the electron is. Now, does that mean I know exactly where it is? No, I don't. Okay, but I can get an idea of where I think it's going to be based upon the shell of the sphere here. So I could say, for example, with 99% probability at any given time, the electron will actually inhabit the inside of the sphere here. Okay? Now, is the electron somewhere else in the next moment? Yeah, it could be here. In the next moment, it could be here. In the next moment, it technically, outside of that 99% probability, could be outside of the sphere. Okay, but I could say within 99% probability, at any given time, that electron is inside that sphere. And that sphere now is a 3-dimensional region in space, which I'm going to call an orbital. Okay? So another way of thinking about this is you can think about this being sort of a house, right? So you could tell, for example, that somebody enters a house, but if the shades are drawn, you don't know where in the house that person is, right? The person could be in the living room, the person could be in the dining room, the person could be in the kitchen or the bathroom. We don't know. We just know with some degree of certainty that the person is in the house. So that's the same sort of idea that I'm employing here. I can't tell you at any given moment where the electron is, but I can say with some degree of certainty that it's inside this 3-dimensional volume defined or scribed out in space. All right? So we're going to build on this and learn more about the quantum numbers next time in class. So we'll see you then.